Hello, Daniel, Blake. It's good to be back with you guys again looking at some math. So I hope you guys are doing well. And we're going to go ahead here and we are going to start in continuing along with 16.4. So we left off with 16.4. We're going to continue with 16.4. And the truth is, looking at those surface integrals, the truth is today we really don't have any new learning. We're just applying it to more situations, and so I don't have any additional notes for you, just a couple examples of how to do some of these, and so let's take a look. So first example we're going to look at is number 22. So number 22, it gives us the following equation of a plane. So that's identified as a plane. It's a plane in the three-dimensional space there, and we're told that we want the surface integral there of that plane that's bounded by this cylinder. So you can think there's a cylinder going there right around the z-axis with the z-axis through its center, radius of 1 on our cylinder there, and we want the portion of plane that is inside of that cylinder. That cylinder provides the boundary, and then we want to get the surface integral over the function that we're given z squared. So that's our function. So this one lends itself to being solved. Start off with our general expression here where we know that z, what we want to do is we want to solve it where we want to express our g of uv is essentially a function f of x, y, and then a function where z is expressed as another function g of the xy. So we have to solve for z so we can express it in terms of xy. So z is going to be negative x minus y. And then that leads us to our g of xy function is going to be, since that's negative xy, that's going to give us that our partial with respect to x is negative 1, and our partial with respect to y is negative 1. So from that, now we can go ahead and we know we're going to have this integral over the surface, and we know our x, our f of x function, we're going to express as f of x, y, g of xy. So now we've got it down to two variables, and that's going to have to be, when we do that conversion of the variables there, we have that factor there, which is our magnitude of our normal vector ds. So that magnitude of our normal vector ds there just becomes the following expression. So as we go ahead and substitute in, we get this, because we know this here is going to be radical 3. Now the last thing that we have to do is we do need to, problem is here, this is in terms of x and y, and I don't know limits for x and y here, given this situation. So what I need to do is, the easiest way to do this, since this is a cylinder here, is to change it into polar coordinates. So changing to polar coordinates, I know that the boundaries for that cylinder are going to be where theta goes from 0 to 2 pi, produces the whole cylinder. My r value goes from 0 to 1. And then notice what I've got. I've got this radical 3, and I will re-express this with x as r cosine theta and y as r sine theta. Square that. And I have to add my r and then my dr d theta there as I change the two variables. So now I've got, and actually, you know, I'm thinking I have something that's a little bit wrong here. This here actually has become, let me double check, I think I've got something wrong in my formula. A misapplication here I've written down. Yes, this is no longer d. This is now, after I've done this, this is over the restricted domain, and this is actually now our dx dy or dy dx, however you want to think of it. This is our d, and this is our dx dy or dy dx, doesn't matter which. So now it's when we've converted from dx dy into polar coordinates, we have our factor of r dr d theta. So from that, now we can go ahead and we can go through and do our process of integration. So first thing we want to do, factor out that radical 3, then do the actual expansion here. So I get, this is going to be r squared cosine theta, r sine, whoops, I'm missing my, oh, that's cosine squared, I'm missing my squared there. And then I've got r cosine theta, so I got negative times a negative here, so I've got r squared cosine theta sine theta, but I've got 2 of them because I got an inner and an outer, so that's 2 of those r squareds cosine theta sine theta. And then finally I got plus my r squared sine squared theta, and that's r dr d theta. Well, factoring in r squared out of each one of these terms here, I get an r cubed, and then notice what I've got left inside is I've got a cosine squared plus a sine squared, that's just 1, plus 2 of these cosine theta sine thetas. And that's now, notice the r cubed comes from multiplying by that r, and so that's dr d theta. Now I need to do the integration here. Probably easiest, at this point here, it's probably easiest to recognize. Now I could use u substitution on this. I could let u be sine of theta, du would be cosine of theta, and go like that. But also we could just recognize that this is just, this is our formula for sine of 2 theta. So we can simply replace that with sine of 2 theta and break it up here into 2 separate integrals. So since this is r and it's multiplied by this expression with no r's in it, I can break it up and have r cubed with its limits 0 to 1 times the integral 0 to 2 pi of the expression that has theta as its limits. And I've replaced that 2 cosine theta sine theta with sine of 2 theta. So now going ahead and integrating. So integrating this, I get 1/4 r to the 4th, and that's evaluated from 0 to 1. And I'm going to multiply it by integrating this here. I will get theta, and then I will get end up with a minus, and I'll have a 1/2 cosine 2 theta, and that's evaluated from 0 to 2 pi. Now doing some evaluation, I have radical 3 times. This one's pretty easy to see that it's going to be just 1/4. 1/4 is now multiplied by this thing here. So when I put in 2 pi, I get 2 pi minus, putting in 2 pi here, that becomes 1, so that becomes minus 1/2, minus, when I put in 0 in there, I get 0. When I put in 0 in there, I get a minus 1/2. So notice what I end up getting here. I get radical 3 times 1/4. And if I look in here, the 1/2s cancel because I've got negative 1/2 plus 1/2. I just have 2 pi. So simplifying down, looks like I get pi radical 3 over 2. And that's my answer. All right, now let's look at one that's a little bit different because this one is going to be part of a sphere. So we're told that we have the unit sphere, and they don't give us the equation for it. I wrote that down. The equation for the unit sphere, x squared plus y squared plus z squared equals 1, centered at the origin. Next, we're told that x is greater than 0, and we're told that the absolute value of y is less than or equal to x, which means that negative x is less than y is less than x. So these become our constrictions for our particular domain over which we want to integrate. And we are also given a function. Our f of x, y, z is just equal to x. Now this is a little different. This is one where we are going to want to change this into cylindrical coordinates. Spherical coordinates as we do this. But we're not going to turn it into f of x, y, g of x, y. We are going to go ahead and we're going to change the coordinates before that. So what we're going to do there is we're just going to define this in terms of a function g in terms of theta and phi. So we know that when we have the unit, what's going to produce this unit sphere is our r will be 1. So the nice thing is we got 1, so it's going to be 1 times cosine of theta sine of phi. Our y component is going to be sine of theta sine of phi. And then our z component is going to be cosine of phi. And our radius on each one of those is 1. So that's just simply, so I didn't have to express this as g of theta phi and then another function, some function of theta and phi for z. I could just go directly to spherical coordinates right there, expressing the whole thing in terms of theta and phi. And so if it was, if the r was varying, then I would have a variation in the r, but the r is not varying here. So I just got my theta, my phi, and my, and that's it. So because of that, let's look a little bit more about what we're really talking about here. So let's get our limits of integration. So what we're really talking about, if I look at this, is we can imagine the unit sphere in the xy coordinate plane. We're talking about, notice, x positive. So we need to be going this direction here for where x is positive. But we're also talking about y's that are bigger than negative x, which means we're talking about going this way from those. We're talking about y's that are less than or equal to x. So y equals x is that line there. So we're really talking about this region that you can see in there. Well, notice when I go to describe that, notice what it's going to do is it's going to restrict my theta. Remember, my theta is the measurement of the angle in the xy plane to negative pi over 4 to pi over 4. So that ends up restricting my theta there to negative pi over 4 to pi over 4. My z, on the other hand, I'm still is going to be talking about, as z comes up this way, I'm still going to be talking about the movement going from here, going from 0 all the way down and around, because it's that entire half loop there of the sphere. So my phi angle is still going to go from 0 to pi. So with that, I can now set up my equation. Now, because I went and I substituted and went to, did not express it as g of theta, phi, and then some function of theta and phi, I don't use, if you look in your book, I don't use the formula 9. That's the one for where it's of f of x, y, and then some g of x, y. I'm going to go back and I can use the form there that is the form 7, which is that direct fundamental theorem form there, where my function there is already given in terms of a parameterization. So doing that, the key thing is, though, I do need the magnitude of my normal vector. Now, you could go ahead and calculate this, but that's a lot of work. We're going to save ourselves the grief here by looking at what is in our books, by looking at what is equation number 2. If you go back and you look at equation number 2, you'll see that when dealing with a sphere, our normal vector is r squared sine of phi. So our r in this case is 1, so it's 1 squared sine of phi, which is just sine of phi, and that's from equation 2. And that makes it nice because we know it's a sphere, and so it makes it very nice to get that. By the way, that r squared sine of phi, remember, that's the norm, but that's the naturally occurring thing that if we were to do a switch of variables, we would have to remember that we would have an r squared sine of phi as a factor. And that's where that r squared sine of phi comes as a factor. It is actually the magnitude of that normal vector. So that's where that would come from. So you could think of doing it that way, and then you'd have to add your r squared sine of phi, which in this case is going to add this, which is just going to be that. Or you can just go to the formula. So now I can just express it as the parameterized function. So our general integral is going to be over our specific domain with our parameterized function. There, our function expressed in terms of our parameterized function. Remember, our parameterized function is this right here. That's our parameterization there. It's actually, and then this is going to be times our norm, which we know, not our norm, but our magnitude here. And it's our du and v. Of course, here, our u and v are going to be theta and phi in this case, because that's what we parameterize this with. So doing that, I get negative pi over 4 to pi over 4, 0 to pi, and notice what I've got. My f of xy was just x, so my x is just cosine theta sine phi, and that's going to be multiplied by my sine of phi, and now I put in my d phi, d theta, making sure to match these up with these here. Now it's just a matter of integration. So going ahead, re-expressing here, multiplying there, I get a sine squared phi. Once again, easiest to break these up into two separate integrals. Take the theta factor and integrate the cosine of theta, going from negative pi over 4 to pi over 4. And then integrate from 0 to pi of the, and I re-express the sine squared phi. I use my double angle identity there and re-express it as 1/2 times 1 minus the cosine of 2 phi. Now I could go ahead, d phi. Now I go ahead, do the anti-differentiation. So the antiderivative, this is the sine evaluated from, and I forgot my sine of theta. The sine of theta evaluated from negative pi over 4 to pi over 4 times 1/2. And when I anti-differentiate this here, I get theta, or phi, sorry, it's phi. And then when I do this one here, I get minus, and I would get 1/2 sine of 2 phi, and that's all evaluated from 0 to pi. So now I can go ahead, substitute in. I got the sine of pi over 4, which is radical 2 over 2, minus a negative radical 2 over 2, which is plus radical 2 over 2. That will be multiplied by 1/2. There's my 1/2 times, when I substitute pi in here, I get pi minus 0. Put in 0, I get 0 minus 0. So it's all minus 0. So I end up with radical 2 times pi over 2, which ends up being equal to pi radical 2 over 2. Okay, there we go. Have at it and enjoy. Assignment is 6.4, 21 through 29 odd. Hope you guys are doing well. And we will have a Zoom session on Thursday if you guys have questions. All right, talk to you later. Bye.